So at long last we discovered planets around normal stars. Or had we? I mean, there was a lot of reason to be sceptical about these things, and in fact a large fraction of the astronomical community were really not convinced. There had been too many false alarms in the past. What we really needed was some independent confirmation.
Exactly. Certainly from my own experience, you need to have two teams looking at something that's really controversial for people to believe. And in this case, a team in California had come up with a novel idea to really make sure that they didn't have any what we call systematic errors. Because if you remember, when you need to measure these tiny little velocities, any little tiny glitch will give you the wrong answer. And so what they decided to do is they put a glass cell full of iodine. And now iodine has lots of spectral lines, like thousands upon thousands of them. And they're very narrow. And they put it before the light entered the spectrograph. And so as the starlight shone through this iodine cell, it had imprinted on it each of these lines of iodine, which could act as a reference stick for the wavelength of the light.
So the spectrum you see at the end here would have both the lines from the star itself and the lines from iodine. Now the iodine cell is not moving, so if the spectrograph was all perfectly stable, they would always be in the same place. In practice, as the light lands on different parts of the slit, or the temperature or the pressure change, or any of the other things that could go wrong, that would cause the iodine lines to shift a bit, but it would shift them by the same amount it would shift the lines of what you're looking at.
That's exactly right. So it was a way of getting rid of all those nasty little problems. The trick is these iodine cells are messy, and they really do make a nice looking spectrum and make it look terrible. So it's very difficult data to analyze.
A lot of hard work had gone into the software.
Yes.
But nonetheless, the Californian group of Paul Butler and Jeff Marcy had been working on this, and in fact they actually observed 51 Peg. They just hadn't analysed the data, because after all, no one was expecting planets. They didn't think we could see planets like our own solar system. But as soon as they heard the result from Switzerland, they of course immediately went back and analysed the data, and they found the same thing. What's more, when they dug through more of the data, they found more similar sorts of signals. So at long last, we had confirmation.
And we didn't just have one object, we had a whole bevy of planets suddenly come from essentially nowhere in a very short period of time.
So here were the three problems we thought. The first problem, were the data valid? And the fact that we've now got two groups using different methods. So we have the Swiss group who are using the fibre optic cable method, and we had the California group using the iodine cell method. And they both observed the same thing and saw the same velocities at the same time on different telescopes and different methods. So that's telling us that this is very difficult observations, but clearly they're getting it right.
So Paul, we still have that problem of potentially the object just being a brown dwarf nearly face on, so you only get tiny orbital motions.
So it could be that the motions are real. In fact, they probably are now. We have two groups finding it, but maybe it's not a planet, maybe it's a star. And of course, we've known about binary stars for a long time. But the more you discover, the less likely that becomes. Because if you imagine, let's say you have something really massive going around like this. If it's face on, most of the wobble is going to be out of the, not on your line of sight, so you're only going to get a very small fraction of it. So it look like a planet. But for everyone that's going to be face on, there are going to be many more that are at some other angle. And for these ones, you're going to see a huge oscillation. And so you'd expect maybe for every one that looked like a planet, you'd see 10 or 20 that looked like brown dwarfs. And you won't see anything like that many, these huge oscillations that could be brown dwarfs. So with just one, maybe it could be a fluke. It happened to be in face on very close. But by the time you've got 3 or 4 or 5, let alone the hundreds we've got now, that doesn't make sense. Any individual one of them still could be, but as an ensemble, the whole population, no.
Okay. So what about the idea of it being some sort of stellar pulsation, like a Cepheid variable star, but something a little different, that just mimics the sine wave of a planet?
Well, this was seriously considered. Maybe it was some sort of strange pulsation of the star's surface rather than the actual whole star moving. The trouble with this were kind of twofold. First of all, when you get a pulsation from a star, it's very rarely looks like a sine wave. It tends to be a slow rise and a sharp drop, or a steep drop and a steep rise and a slow fall. Secondly, when stars pulse, they don't just pulse at one period, they pulse at multiple periods simultaneously.
They have a resonance, right? They're almost like a musical instrument that when you play a trumpet, it doesn't just give you one tone, it gives you multiple
It's a whole bunch of
tones.
harmonics.
Yeah.
Only they're not very harmonic, they're all at funny ratios. It would sound horrible if you listen to it. Probably like bagpipes.
Yeah.
Bagpipes and bells are two instruments that have harmonics that aren't nice at regular intervals. But people were only seeing the one sine wave. So that made it very hard to come up with any model of a star that would do that.
Okay. So it looks pretty solid.
And what were they discovering? Well, most of the ones they were discovering were something like this, the hot Jupiter, where a planet's in a near circular orbit very close in. This is a schematic, it's not really to scale. To scale, it looks more like this. There's a dot coming across.
Much less impressive.
Much less impressive, which is why most people don't give you scale drawings of these things.
So were all the objects, going in these close circular orbits?
The bulk of them were, but there was also another class of things, what were called the 70 Virginus systems after the first one discovered, 70 Virginus. And these ones, the planets are actually much further out. This is once again is not to scale. They're actually maybe as far out as the Earth, an astronomical unit out, but they had very elliptical orbits. They came very close, whipped around very close, then way out slowly, then in and close.
So you can really see them when they come close. So the way you find these things is the fact that they are elliptical and they have big radial velocities here, very tiny ones out there.
That's right, at least to begin with, that's how they were discovered.